Hello. Today we are going to take a look at a PowerPoint presentation to help you achieve the following goals. You can see that what we're going to try to do today is show you how to calculate pH or pOH for any strong acid or base. We'll have a separate lesson later to help you out with the weak acids and bases. We are also going to learn how to calculate the hydrogen ion concentration, which is related to the pH or the pOH, but is different. This is how many moles per liter of hydrogen ions are dissolved in the solution, and this is how many moles per liter of hydroxide ions are dissolved in the solution. And then we're going to learn how to classify any solution as acid, base, or neutral, depending on these relative amounts of hydrogen and hydroxide ions, or by the pH or the pOH that we learned to calculate. Let's start off by going back to that very first lesson of acids and bases where we talked about the self-ionization of water, how water can break apart into two ions, the hydrogen ion and the hydroxide ion. Of course, it's a reversible reaction, and the ions can come together to make the molecule. This reaction can be expressed with a equilibrium expression. So we've got, the product of hydrogen and hydroxide on the top, and then on the bottom there's nothing because water is a liquid and we don't include pure liquids in our equilibrium expressions. Instead of calling it a KEQ, we actually just call it, I wrote AQ instead of EQ. But instead of calling it a KEQ, we call it a KW. It's the same thing as a KEQ, but it's just the equilibrium constant for water. And since it's so commonly used, it kind of got its own little symbol, KW. The equilibrium constant for water is sometimes referred to as the ion product constant for water, since it's the two ions multiplied together. But this is the equilibrium constant for water at 25 degrees Celsius, and the value of it is 1.0 times 10 to the negative 14. Yeah, it does change a little bit with temperature, but we are going to do all of our problems at 25 degrees Celsius, which is considered room temperature. And for that, this is the value that we use to plug in here and be able to set up an equation to find the hydrogen or the hydroxide ions in a solution. Here's an example problem. Let's say that we have the hydrogen ion concentration given to us. Ooh, and that's hard to see. Let's pick our color. And if we know the hydrogen ion concentration, we can actually calculate the hydroxide ion concentration and then compare those to classify the solution as acid, base, or neutral. If you remember back in the very first lesson of Unit 12, we learned about how it's the relative number of hydrogen to hydroxide in a solution that determine if it's an acid, base, or neutral. If it's an acid, the hydrogen ions are higher concentration. If it's a base, the hydroxide ions are higher concentration. And if those two ions are equal to each other, then a solution is neutral. So how are we going to go about calculating the hydroxide? Remember on the previous slide that the equilibrium constant or ion product constant for the water is equal to the hydrogen ions times the hydroxide ions. The KW always has the same value, and we know the hydrogen ions, so if we know these two, we can easily calculate the hydroxide by solving for it. So we'll just divide both sides by that hydrogen ion, okay? And we get that the hydroxide ion concentration, that's what the brackets mean, is going to be equal to the KW divided by the hydrogen ion concentration. Now the Kw is 1.0 times 10 to the negative 14. And yes, I got a little random line there. Getting a couple of those today already. And the hydrogen ion concentration was given in the problem. It's 1.0 times 10 to the negative 13. Now you can probably do this math in your head because when you divide 1 by 1, of course you get 1. And you can subtract the exponents and get 10 to the negative 1. Or you can try plugging it in your calculator. But we can see that the hydroxide ion has this concentration in moles per liter. Now comparing them, okay, the hydrogen ion, remember, was 1.0. Darn lines. The hydrogen ion was 1.0 times 10 to the negative 13 as given in the problem. And the hydroxide is 1.0 times 10 to the negative 1. Now, if they were equal, it would be a neutral solution. But in this case, the hydrogen is a lot less than the hydroxide, and that makes this solution a base or basic. Okay? So given any concentration of hydrogen, we can calculate the hydroxide. Given any concentration of hydroxide, we can calculate the hydrogen. Because we know that if it's a water-based solution, their concentrations will always multiply to give us the Kw, which is 1.0 times 10 to the negative 14. Now moving on, you probably are familiar with, instead of calculating a hydrogen or a hydroxide ion concentration, you're probably used to taking something called a pH. A pH is a number scale that is related to the hydrogen and the hydroxide ion concentration of a solution. We'll try to demonstrate that today and show you how they're related. But how you usually take a pH is with some sort of indicator solution or an indicator test strip, where you take a sample of water or a solution that is water as the solvent, and you, put this indicator in that solution, and the indicator comes up a certain color, and you match it up on like a scale, a reference scale. Maybe you've seen people do this with pool water or with fish tank or maybe hot tub. Sometimes there's test strips that you can just dip into the water. And again, whatever color it comes out tells you a pH number. Now, did you notice that the value of the Kw, 1.0 times 10 to the negative 14, and the pH scale goes to 14? That's not a coincidence, okay? Remember, when a solution is neutral, these two, the hydrogen and the hydroxide, are equal. The only way they can both be equal is if they're 1.0 times 10 to the negative 7. And notice that 7 is neutral, okay? This is not a coincidence, because the way that you find the pH is that you take the negative log of the hydrogen ion concentration. Well, if the hydrogen ion is 1.0 times 10 to the negative 7, and you take the logarithm of that, it's negative 7, and you change the sign, you get 7. The pH is neutral when the hydrogen ion concentration is 1.0 times 10 to the negative 7. If you have a higher concentration than 10 to the negative 7, you're going to get a lower pH, which corresponds to an acid. If you have a concentration of hydrogen ions that is lower than 10 to the negative 7, like you have something 10 to the negative 9, then you're going to get a higher number for the pH. And the higher numbers correspond to it being a base. So you can see that there's a mathematical relationship between the concentration of these ions and the pH. Most people don't realize that every solution also has something called a pOH, and that's just very simply the negative log of the hydroxide ion concentration. Remember that when hydrogen is 10 to the negative 7, hydroxide also has to be 10 to the negative 7, and then both of these, the pH and the pOH, come out to be 7 in every solution. Whatever pH value you get and the pOH value that you get, they will equal 14. This is a super handy relationship to remember. You'll see me use this a lot in solving problems as we proceed through this PowerPoint. But just like there's the pH scale, there's the pOH scale. In this one, 7 is still neutral, but now the high numbers are acid and the low numbers are base. So it is the reverse of the pH scale. We already did this problem in red. We calculated the concentration of the hydroxide, and we said that it was a base or that it was basic. Now, let's calculate pH and pOH values for this solution. The pH is going to be equal to the negative log of the hydrogen ion concentration. So negative log of 1.0 times 10 to the negative 13. And when you take the logarithm of this number, you're going to get negative 13. You change the sign, and you should get 13. Everybody should practice punching that into your calculator to make sure you know how to use your calculator. And if you aren't getting that answer, check with a classmate or a teacher, maybe a math teacher if you can't get help in your particular calculator from anyone in this class or teacher in this class. But this solution has a pH of 13. We had said this solution was basic, and that corresponds. 13 is a pretty strong base. Remember that the pOH is the negative log of the hydroxide ion concentration. So negative log of 1.0 times 10 to the negative 1. And when you take the negative log of that, you're going to get 1. Again, that corresponds with the basic answer because low numbers on the pOH scale correspond to bases. And then there's this special relationship that the pH and the pOH always add up to give you 14. And you can see 13 and 1 are going to add up and give you a value of 14. So what are some other things that you'll be expected to do? Well, not every solution has an even pH or pOH number. Sometimes there's going to be decimals in between. Anytime this first number is not 1.0, you're going to end up with a decimal in between two whole numbers. So this says calculate the pH. So we know that the pH is equal to the negative log of the hydrogen. So it's equal to the negative log of 3.0 times 10 to the negative 9. So you want to punch that into your calculator. When I do that, I got a value of, let's see, I got 8.52. You guys will be really glad to know I'm not going to be looking at sig figs. This gets really hard in this unit, just like last unit, to keep track of sig figs. I would suggest, though, that you keep at least the 8.5. I wouldn't think that you want to round that to 9. If you keep 8.5 or 8.52, that looks pretty good to me. Now, as far as classifying that has a pH that is above 7. That means that this solution is going to be a base. When you do the WebAssign, you want to be really careful looking at whether they're using the word base or basic. I do know there's some questions on WebAssign where it marks you wrong. I can't remember which way it is. If they want you to say base, and sometimes people say basic, or if they want you to say basic and people have typed in base. But if they use a certain form of the word, make sure you use that form of the word, because WebAssign is matching up specific answers. If it marks you wrong and you run out of submissions, just see me about that. Now down here, do you see how this is a hydroxide ion concentration? If we're going to take the negative log of the hydroxide, that is going to give us the pOH. So when we take the negative log, and I was doing pretty good. Oops. Did not. There we go. When we take the negative log, my goodness, for some reason, I just can't seem to, hold on. I'm starting over here. So when we take the negative log of the number that's given in the problem, remember that this is going to be giving you the pOH and not necessarily the pH. When I take the negative log of this number, I actually get 5.1, okay? That, remember, is the pOH value. This says to find the pH, and you got to be really careful about that on web assigned 2. Which one did you find and which one are you looking for? If you found one and you're supposed to be looking for the other one, all you got to do is subtract from 14. So that makes it very easy. And in this case, we get a pH of 8.9. Again, above 7, that makes it a base. Low pOH, high pH, this solution is a base. Now, we can also solve our logarithm where if we know the pH value, we can find the hydrogen ion, or if we know the pOH, we can find the hydroxide ion. To do that, we have to solve our logarithm. I'm going to multiply both sides by -1. So that I have negative pH is equal to the log of the hydrogen ion. To solve my log, I take the analog of both sides, which means, and I definitely want to clear that line up because we want this to look appropriate. We need 10 to the negative pH. This is an equation that's going to be really handy. If you know the pH of a solution, like you took some water from your hot tub and you did one of those, match up the color solutions, and it says, okay, your pH is 6. You know then that you can plug 6 in here and calculate the hydrogen ion concentration of the water that's in that hot tub. Likewise, you can do that with the pOH equation. We can solve for our log. This is pOH, then is equal to the log of the hydroxide. Remember, these are base 10 logs. So that's why when I take the analog, it's 10 to the negative pOH, and that'll give me the hydroxide ion concentration. And this was a 0 and not a 6. Again, this is another equation that's going to be very handy moving forward. Okay, let's try them out. So I use a pH meter. I put it into a solution to check and see what its pH is, and it tells me that it's 2.37. From that information, I can easily get both the hydrogen concentration and the hydroxide ion concentration that is in that solution. Remember that 10 to the negative pH will give me the hydrogen ions. So to get the hydrogen ions, I go 10 to the negative 2.37. You want to do that on your calculator. Make sure you know how to use your particular calculator. I can tell you that I see a lot of students sometimes that'll have this correct equation written on a test but have the wrong answer. Again, I'm not going to pick over your sig figs, but 2.37 has 3, so I'm going to keep 3. I got 4.27 times 10 to the negative third, and that's a concentration. When you see those brackets, that means concentration. So that's the concentration of hydrogen ions in this solution. Now, to find the hydroxide, you could take Kw, divide by the hydrogen, or you can take 10 to the negative pOH. Now, if you're sitting here thinking, well, I don't know the pOH, remember the easy way to get it is that the pH and the pOH have to add to give you 14. So if I take 14 minus 2.37, I got 11.63. That's the pOH of my solution. I take 10 to the negative pOH and I got 2.34 times 10 to the negative 12th for the molarity. See, the pH is really low, so that makes this solution an acid. If a solution is an acid, I should indeed come out with a higher concentration of hydrogen ions and a lower concentration of hydroxide. And this is indeed lower, okay, because it's to the negative 12. So this makes sense. This solution is an acid, it has a low pH, and the hydrogen ion concentration's higher in this case than, that's supposed to be greater than the hydroxide. This solution has been verified to be acidic, okay? Now, this says determine the pH of the following solutions. Note they are all strong acids and bases, okay? We'll give you a list in class of the strong acids and the strong bases. There's a short list that you have to memorize, okay? All other acids and bases that are not on that list are weak acids and bases. You can only use this method that I'm going to show you right now for the strong acids and bases. And the reason why is that strong acids and bases, they are the only ones that 100% ionize. If they dissolve in water, it is not a reversible reaction. When a molecule of HNO3 dissolves in water, it breaks apart into ions. Notice that it is a one-way arrow. This is not reversible. When it breaks apart, I only get one hydrogen ion for every one HNO3. Remember back to the solutions unit in Unit 10, where we learned that if it breaks apart and it only makes one, then the concentrations, they're on a 1-to-1 ratio. So the concentration of the hydrogen ion in this solution is 0.50 because when this breaks apart, it only gives you one hydrogen ion for each mole of HNO3. So that makes it easy now. The pH is equal to the negative log of the hydrogen ion concentration. I calculate this, and I got a really small number. That's because HNO3 is indeed a strong acid. I got a really low pH. Now I'm going to switch colors just so I can keep them all straight. But sulfuric acid is also a strong acid. So the arrow is going to go one way. Every molecule that dissolves breaks apart. Do you see that you get 2 hydrogen ions, though, for every 1 sulfate ion? When I have a molecule of H2SO4 and it breaks apart, I get 2 hydrogen ions. 1 particle of H2SO4 produces 2 hydrogen ions. So remember that from the last unit? I got to double this. My hydrogen ion concentration is 0.070. So when I find the pH, that's the concentration that matters. I know that the sulfate is only going to be 0.035. Doesn't matter. It's not the anion that makes something an acid. It's not the anion that gives it a pH value. It is only the hydrogen ion and the concentration of the hydrogen ion that matters. When I solved this one, I got 1.15 or 1.2. I wouldn't round it off any more than that, though. Now, you might be asking, how is a weak acid different? Wouldn't I just look at how many H's there are? But remember, if it's a weak acid or a weak base, you remember how it does not completely ionize and we cannot use, excuse me, I didn't say weak acid, I meant to say, if it is a reversible reaction, okay, we cannot use stoichiometry. Arrow goes one way, we can use stoichiometry. Arrow goes one way, we can use stoichiometry. Now, is what I meant to say, if it's a weak acid or a weak base, it's going to have a reversible arrow, and we cannot use stoichiometry when it's a reversible arrow. We have to apply the principles of equilibrium that we learned in Unit 11. So when you are working on problems, it is very important, is it strong or is it weak? Because it absolutely has to be strong acid or base for it to be completely ionized, and use stoichiometry to figure out the hydrogen ion concentration and thus the pH. Now, calcium hydroxide is going to be on the list of strong acids and bases that you are given. When it breaks apart, and this is why we practice this a lot in Unit 10, you get one calcium ion and you get two hydroxide ions. Ignore that line up there. You can see that for every one calcium hydroxide, you get two hydroxides. So I'm going to double this. Just like I did in number 2, I'm going to double this, and that is going to give me the hydroxide concentration of, 4.8 times 10 to the negative 5th. Now, when I take the negative log of that, I'm not getting the pH, I'm getting the pOH, because that is hydroxide. Remember that hydroxide gives you the pOH. So I got 4.32 as the pOH. And you say, well, I need the pH. I mean, this question, you look back at the beginning, determine the pH. If you need the pH and you've got the pOH, all you do is subtract from 14. So 14 minus 4.32, and 14 minus 4.32 gives me a pH, and I'm running out of room here. It doesn't want to let me write, but it's a pH of 9.68. Now that pH is above 7, which indicates this is a base. That's right, because this solution has hydroxide ions in it. Remember, the Arrhenius definition of a base is something that breaks apart to make hydroxide. The first two, number 1 and number 2, they had low pHs. They were acids. That's right. The Arrhenius definition says an acid is something that breaks apart to make hydrogen ions. So hopefully that makes sense. And you now know how to calculate the pH or the pOH. pH is negative log of the hydrogen ion. pOH is negative log of the hydroxide ion. If you take 10 to the negative pH, that gives you hydrogen. 10 to the negative pOH gives you hydroxide. Of course, you can always relate these two by the fact that their product is equal to the Kw. So if you know one of these, you can always find the other one as well. And now you also know two different ways that you can classify. Okay, an acid has hydrogen ions greater than hydroxide, or it has a low pH or a high pOH. For a base, there's less hydrogen That's random. Then there is hydroxide, or it's going to have a high pH. And if it's neutral, the hydrogen is going to be equal to the hydroxide, and the pH is going to be 7. Because the only way for them to both be equal, yet also have a product of 1.0 times 10 to the negative 14, is that they both have to be 1.0 times 10 to the negative 7, which means the pH is 7, the pOH is 7, and of course that'll be a neutral solution. So hopefully that helps you out with, how to do these things. There's going to be homework problems and problems on WebAssign to do in class and for homework to help you practice this, okay? And if you need help, of course, please ask. I am glad that you were able to tune in for this, and I certainly hope that it helped. And there we go.